I'm Pavlo from Carnegie Mellon University, and today I'm going to be talking about the long struggle that has occurred between database systems and operating systems. And for the last 50 years, operating systems have been making the lives of database engineers absolutely miserable because the operating system is making certain design choices and imposing its will upon any user space application like a database system. And oftentimes those decisions are not in the best interest of not actually what database systems want. So today I'm going to be talking about some work we've been doing at CMU for the last couple of years that we think is a step in the right direction to begin to alleviate or right this historical wrong. So before we get into that, first we want to understand, well, why is it that database systems hate operating systems so much? And if you go back to some of the earlier papers in the 1970s, 1980s, you see a lot of discussions about how there's certain things that the operating system wants to provide, certain services, like how to manage memory, when to write files out of the disk, that is actually the opposite or oftentimes incorrect in terms of what the database system needs to provide to ensure transactional support and other guarantees. And so there's this seminal paper from Mike Stonebraker, inventor of Postgres and Turing Award winner, where he talks about how basically what the operating system wants to provide for in terms of services is either being too slow or just simply semantically incorrect for what the database system wants. And it doesn't help that the operating system people actually have utter disdain and don't like database people either. Right? You don't have to look very farther other than Linus, the inventor of Linux. He makes it very clear he has little regard for what database systems actually want. And so there's this mailing list post from about a decade ago when they're discussing fixes for asynchronous I/O, which is something database systems absolutely want because you want to be able to write things out and in a non-blocking manner while your worker thread does other work. And he's saying, well, this API is horrible, and we only have to maintain it. Linux only wants to keep maintaining it because database people, which have bad taste anyway, they're the only ones actually using this and actually want it, right? So we're not getting any help from operating systems, even though there's things that clearly would be better for us in the database world. And so you see things when you look at the source code of your favorite database system, where oftentimes there's a bunch of workarounds and additional accommodations just because the operating system is going to do something that is actually the data system doesn't want it to happen. So if you go look in the Postgres source code, there's this comment in here where they talk about how they have to do a bunch of extra work because in Linux, the out-of-memory killer is going to decide to kill the postmaster because it's going to assign all the additional memory of its child processes in shared memory to the parent process, and says that's the one that it should be killing, which is actually the wrong thing to do. And so they have a bunch of workarounds that deal with this. Right? Pick your favorite system. There's probably going to be something like this in there. All right, so what are we supposed to do as database system engineers? Well, the best we can do for conflict is try to avoid it as much as possible, right? And let's be honest here, database systems are the most important software in the world, right? And they're beautiful pieces of software that all they really want to do at the end of the day is what the core of computer science is, right? Take some input, do some processing, and produce some output, right? So they want to help people store their data, want to help people run queries on the data, right? That at the end of the day, that's what they really want to do. And the operating system's coming down with this iron fist and saying, no, you got to do it our way, all right? And just making our lives absolutely miserable. And I would argue, again, database systems are the most important class of applications that are out there, right? Name me another class of applications or code that has helped somebody buy a Hawaiian island, right? There isn't anything. So at the end of the day, if we know the OS is all they want to do is crush the will of our beautiful database system software, we have to decide how are we going to kind of overcome this. So the core tenet in designing a system is that you want to try to avoid having your data system talking to the OS as much as possible, typically through syscalls, and just try to make sure that the operating system doesn't get in the way of what you want to do. Okay, so how do we actually do that? Well, there's two approaches to try to avoid talking to the OS. One of them is going to be through a technique called kernel bypass, and then another one will be called user space bypass. So I'll go through each of those one by one. So the idea of kernel bypass is that you're going to take these operating system services that are not what the data system actually wants, and you're going to put it inside your database system. And that way you avoid this extra copying and this back and forth between the OS and the database system. Right? So at a high level, you sort of think of like in the networking stack of your data system. You have a client at the bottom. It's sending requests up for queries and data that goes through the OSes networking stack in kernel space, and then it trickles up into the user space of the database system. So with kernel bypass, the idea is that you want to take a bunch of this logic here, because this is all implemented inside the kernel, and you want to put that now inside your database system, right? So it sort of roughly looks something like this. There's a bunch of libraries that are available that can help you do this. DPDK and SPDK are both things that Intel put out over the years. And these are, again, these are support libraries that allow you to have your user space application, your database system, communicate directly with the hardware in some cases. So this seems like something like absolutely you would want to do, right? Well, it turns out it's actually really challenging to implement in practice, and very few database systems actually implement this, right? So the first problem you're going to face is that everything now that used to be an OS service, now you have to re-implement up in user space in your database system. So there's libraries in terms of like for TCP/IP, like FStack, where they've actually just copied out or extracted out the TCP/IP stack from FreeBSD and now have that running as a user space library. But getting that working correctly and performing well is really, really tricky, right? And there's a bunch of horror stories out there that are on the internet about people struggling to try to get good performance using something like DPDK or SPDK. One of my favorite ones is this GitHub issue for another academic project that did some experiments with SPDK, and the SPDK guys saw that and said, "Hey, you're using SPDK entirely incorrect, and that's why you're seeing poor performance." But again, if you have to rely on the library developers to tune and fix your implementation to make this actually work, then that's pretty much a non-starter for most database systems. So as far as I know, there's only 2 systems that I know that actually use kernel bypass. One is Yellowbrick, and then the other one is ScaliaDB, which is sponsoring this conference. But as far as I know, in their C-star framework, they turn off DBDK. They don't use it in production because it's just so unwieldy. Probably my favorite metaphor about why SPDK and DBDK are bad ideas are from Jens, the inventor of IOU-ring in Linux. He likens it basically, if using these libraries, when you're cold outside, it seems like a really good idea to pee your pants because you warm up right away, but then fairly quickly you start realizing that it was a big mistake. All right, so instead of putting the operating system inside the database system, what if we did the opposite? What if we did something called user bypass, where you put the database system now inside the operating system? So again, going back to my example before with the networking stack, if we now take the logic that we have in our data system to process queries and store data and do whatever else our data system wants to do, what if we now inject that now inside of the kernel? And then now when we start processing data and incoming requests come in, we don't have to copy things all the way up to user space, do some processing, and then push it all the way down, right? So we can avoid extra copying buffers or copying buffers back and forth. We can avoid the overhead of switching into privilege mode when we make syscalls. Everything is now directly inside the kernel. All right, well, easier said than done, right? This seems like a great thing to do, but how can we actually do this without resorting to a heavyweight approach like kernel modules? Right? Kernel modules will basically allow you to link any shared object into your Linux kernel, but that's very error prone. If there's a bug in your kernel module, if you crash and you have a kernel panic, and then in some cases, if you're running with secure boot, you can't even load in random. You don't even want to load in random binaries into your kernel because that would be considered unsafe. Well, the good news is for the last decade or so, there's been an execution framework called eBPF that solves this exact problem, that makes it easier for us to extend the kernel with our database system logic that we want down there. So again, we don't have to go talk to the OS for a bunch of things. So the way eBPF works is that the database system developer would build out the logic that they want to inject in the kernel using eBPF's libraries. And they allow you to write these event-driven programs, and you can then attach them to different points in the, for different types of interrupts or to trace points inside your application code. And so you write all your database system logic into C, right? And then you compile them into the eBPF bytecode. And then at runtime, when you want to load them, it then gets passed to this verifier. We have to then go through a bunch of additional checks to make sure that BPF makes sure that your program is not going to cause any issues and doesn't invoke instructions that you're not allowed to call. So I'll talk about what some of these constraints are, limitations are later on. But in general, think of it, you can't call malloc down in your program because you don't want to be, you don't want your thread is allocating whatever memory it wants, and then you run out of memory down in your kernel, right? So everything has to be sort of statically checked and typed, and memory has to be pre-allocated accordingly, right? All right, so this sounds great and all, but how do we actually now take something like BPF and leverage it inside of our database system to get better performance? So what this talk is really about is sort of two categories of systems you can build by using a user bypass method of injecting data system logic into the operating system. So I'm going to first talk about how to do this in a stateless system, like a proxy, and then we'll talk about how to build a more full-featured system where actually the state of the database is actually now being stored entirely in the kernel using BPF. So let's first talk about how to do proxies, and then we'll come back and see how to do this to build a fuller system. All right. In case you're not familiar with what a proxy is, these are very common in real-world database system deployments, especially with something like Postgres, who doesn't always do a good job managing connections. But the basic idea is that normally your applications or clients would be connecting directly to the database system, right? They would open a connection, and then the database system would manage that state for every single client that connects to it. But you may want to also put a proxy in front of it, where all the clients then connect to the database system, but then the proxy can maintain a limited number of connections open to the database system, and it can interleave and multiplex query requests and responses over this single connection. And this is really useful, especially in like serverless environments where you're invoking Lambda functions, where these clients may be coming and going very quickly. And so all the burden of establishing connections is done on the proxy level, and the proxy maintains an open connection, a long-running connection with the database system, and that alleviates a bunch of the pressure on the database system. So if you're going to build this in a traditional manner using user space code, it's going to look like the network stack that I showed before, where requests come in from the client, and once it lands on the server of the proxy server, it's going to go through the operating system's networking stack. And there's a bunch of mem copies as you go up just to get a user space in order to do simple things like look at the message header to figure out what connection you need to send this request to. Right? And then it gets copied back down to the database server. So research has shown that about 50% of the overhead of the Linux networking stack is all in this layer right here, being spent just doing mem copying of the buffers back and forth between user space and kernel space. Right? So that's obviously a big bottleneck for a proxy, where it's pretty much just doing simple processing, like just forwarding requests. There isn't any heavy computation being done. So this bottleneck here is going to be a big problem for our system. So the idea, again, using this user bypass methodology, we want to figure out what's the most frequent operation we're going to do inside of our database system, and then we're going to implement that as a BPF program to embed now inside of our kernel. So we built a proxy based on this. It's called Tigger, and this is based on a fork of PG Bouncer, where we ripped out a bunch of the most common code paths of just forwarding packets, rewrote those as BPF programs, and stuck that down into the kernel. And we actually expanded the functionality of PG Bouncer to include other things like partitioning and workload replication, things that exist in other proxies like PG Pool and whatnot, but weren't available in PG Bouncer. And so what's interesting about this is that there is still some operations or functionality in PG Bouncer that we keep in user space. So for example, things like authentication or updating settings, all that still resides in user space because it doesn't occur that often. And some of the computation that occurs with those operations, you can't easily re-implement in BPF. Like to do encryption or do password authentication. All that code already exists in PG Bouncer, so we're just going to piggyback off of that, and it only occurs every so often, not as opposed to not forwarding packets. So therefore, it's better just to keep that in user space and reuse the implementation. So we measured to see how I did an experiment to see how well our user space BPF version of PG Bouncer compares to the original implementation of PG Bouncer, as well as this other Postgres proxy called Odyssey, which came out of Yandex, which is a rather really sophisticated system. Like for example, they implement their own coroutines using assembly to swap the stacks out of threads to change their context, not using like a built-in coroutine library. It's very impressive, but it's a very complex system to build and maintain. So for this experiment, along the x-axis, we're going to increase the size of the EC2 VM that's running our proxy, and then the y-axis, we're just measuring how many transactions a second we can push through the system. And for this, it's YCSB, so the transactions are not too complicated, but still most of the computation, most of the work is being done through forwarding the messages and not necessarily running the queries. So the first thing to point out is on the smallest instance size, you can see that using Tigger with these BPF programs or functionality, we get 40% higher transaction throughput than the other implementations when there's a limited number of CPUs. So PG Bouncer is a single process implementation. Odyssey is multi-threaded, but again, if you have a small number of cores, then the additional multi-threading doesn't help. But because there's less overhead of our kernel threads running to forward the packets, we're able to achieve much higher throughput. And then when we look at the full spectrum of all the machines, the sizes, you see that in order for Odyssey to achieve basically the same performance that we get on the smallest machine, you got to go up to the eight times larger. So this machine costs 8 times as much just to get the same performance we were getting down below. And again, this is because the work we're doing over and over again in these BPF programs is so simple. Look at the header, figure out where it needs to go, and just forward it right away. Because we don't have to pay that cost to copy things up into user space, we're able to achieve much better performance. All right, so since we know how to do this for proxies, let's see how we now build a more complex system using entirely in BPF, and how do we overcome some of the challenges we're going to hit with the verifier. And I will say too, the first implementation we built in the research lab of trying to use BPF to optimize database systems with this proxy, this was a few years ago. And over the years, the BPF API has gotten much more complex and much more expansive. There's more things we could do now with BPF, and that's why we could build a full-fledged system today, whereas 4 or 5 years ago, this wasn't possible. So we've been working on a new in-memory key value store system called BPF-DB. And the goal is this: to provide a transactional storage engine with a simplistic API for sets and gets wrapped up in transactions, and allows us. The idea is that we're going to allow developers to build more full-featured systems using BPF-DB as the backing storage. So think of something like RocksDB, where there's a bunch of database systems that have built larger, more complex systems using just RocksDB as the backend, and they build all the more complex functionality on top of it. CockroachDB did this, TiDB did this, right? So it's sort of in that idea, but the idea is that that full-featured system could be running in BPF now and talk directly into our data store. We're also going to support a pluggable wire protocol handler, meaning out of the box it'll support Redis, but if you want to support SQL and other protocols, you can just replace these protocol handler components with your own implementation that you would want. So without BPF-DB, what would you actually do? Well, you would use these low-level APIs that BPF provides you to do updates and lookups into these BPF maps. So think of these are kernel-resident hash tables that are only in memory, so they're entirely ephemeral. And this is the only way you can actually store data dynamically inside a BPF program. Again, you can't call malloc, you can't allocate anything on the heap. Any data you want to persist after one invocation of the program to the next has to be put into this BPF map. So the idea with BPF-DB is that we replace that low-level API for just lookups and updates with a more full-fledged system that you can do multi-statement transactions, you can do gets and sets on single keys, and then BPF-DB is going to handle all the storage, transactions, garbage collection, write-ahead logging, all the things you would expect in a modern database system. Now, one of the things that we're going to talk about in a second is that we actually have to bring back the user space components because you can't have BPF programs commit any disk I/O. So you can't read from disk, you can't write from disk. So in order to make our data system durable, we are going to have to push some data up into user space and then do background writing. We'll cover that in a second. So BPF-DB sort of encompasses everything seen here. So now the challenge is going to be, how do we make this work in the context of the verifier's limitations? Again, the verifier's job is to make sure that your BPF program that you're trying to load in the kernel isn't going to do something weird like spin in a for loop forever and lock up the system. Because again, BPF programs are running in non-preemptible mode. So if it gets stuck in a for loop, the OS is not going to have an easy way to go ahead and kill this and clean these things up. And so they're going to do basically static analysis to explore all possible branches, all possible loops, and just count up the number of instructions they expect you to invoke in the worst case scenario. And if you exceed the limit of 1 million instructions, then they won't. You're not allowed to run this program. You can't load your BPF program, right? So this means you can't have unbounded for loops. You always got to put bounds on things, or unbounded while loops, right? You have to guarantee that your program is actually going to terminate. So to overcome this 1 million instruction limitation, which again can get burned up pretty quickly because the compiler can do a bunch of things that can cause problems for you, that we're going to rely on a technique called continuation passing, where we're going to allow BPF programs to basically daisy chain themselves together to have one BPF component or one BPF program call into another BPF program, and it doesn't return, right? So it's a tail call. It invokes it, passes some context, and the execution keeps going. And the idea is that we can chain a bunch of these separate programs together, and each of those are going to be some small sliver of the data system's logic, but all together and execute it in the correct order. Then that will be able to implement the full functionality we need in our database system. So BPF allows you to do 32 tail calls, and that's roughly enough to do a full-fledged system. So it's interesting because again, these restrictions of the verifier causes us to make some pretty unconventional design decisions for a system, which I find is fascinating. All right, so let's go through an example of how this works. So say we have the client is going to make a get request on some key foo. And the first thing it's going to hit is our BPF program that does the protocol handling. So it's going to first parse the request. In this case, it's the Redis protocol. So just looking to see whether your command is get and set. If it's invalid, then it responds an error. If it is valid, then it's going to store the request context that you're looking up the key foo in a BPF map that's tied to this connection, and then invoke through the tail call the data system processor that does the get command in the context of an auto commit. And then the get command is going to know to say, okay, I need to go down to the map at this location, and that's going to give me my execution context that was set by the preceding call. And then we do a lookup in our map to see whether the key's there. If it's not there, we return a nil or not found. Otherwise, we want to return the value. So again, the get command will go to the map, get the data, store it in the context, and then now the responding call knows how to send it back to the client. So how you actually want to store this data is actually pretty interesting, because again, we want to be able to store variable size keys, but again, since we may not know the size of the key ahead of time, how do we handle that without trying to allocate all possible memory on the machine, right? Because again, you can't call malloc on the fly. So what we're going to actually do is have a sort of global index map where for a given key, we're going to store some metadata about different versions of the key and some lock information. But then it's going to have a pointer to these segmented maps that store the actual values. And this will be sort of similar to a slab allocator, where we'll have a map for 8-byte values, map for 64-byte values, and so forth. And that way, you store it in whatever the ceiling of the size that you actually want to store. And that way, we're not allocating more memory than you actually need. And these things can dynamically grow over time. But then now inside this metadata here, this is where we're actually going to store the transaction information that's going to allow us to do multi-versioning and do full-fledged transactions in our system. So at the header of this entry, we're going to have obviously the key that we're trying to look up. Then we'll have the counters for the read-write locks, how many threads are doing reads and writes on the data. And then we're going to have this array, the version array, where it's going to keep track of the timestamps and pointers to what map has the data for this given for the given key at a given timestamp. And so this is a bit different than how a regular data set would implement multi-version concurrent control, because you would have a variable length version chain through pointers, think of like a linked list that you keep appending to as you add new versions. But again, we can't have unbounded linked lists in BPF, so it's a fixed length array. So now when I'm going to try to find what version I want for my lookup, I basically start at the beginning of the array and just scan sequentially, looking at all the version numbers and see whether I find the one I'm looking for. And once I do, then I just follow that pointer to get the data that I want. Now, if you're trying to do a set and this thing is full, you run garbage collection to see whether you can clean anything up. And if there's no more free versions, you basically throw an error. So in practice, we found we can store about 8 versions of this before the number of instructions blows up and goes past the verifier's limit. And again, depending on the workload, depending on the access patterns of the queries, you might need more versions, you might need less versions. Of course, again, it always depends. And then the way we're going to store transactions, or make our transactions durable, is that we're going to have the BPF data system running in the kernel space. It's going to start writing logical log records to say, set this, set that, the actual commands that are being invoked. And that's going to be written to the circular buffer that can be written to by the kernel thread, the BPF program, and read by a user space thread that's just pulling it, looking for new entries. And when it finds one, it goes ahead and writes out to disk. Now, the challenge here is that we can't know when this data has actually been flushed. So when you call commit, if you want to know whether your data is actually durable, you have to come back and ask again, did it actually commit or not? So now this is sort of similar to what MongoDB did back in the day, and people gave them flack for it. But again, this is a limitation of working in BPF, where you can't get notifications that when a flush actually occurs, right? Because you can't block a thread waiting for the flush to finish on commit. But most data systems run with the asynchronous commit terminal by default, so we think this is a suitable trade-off. And then now you have this separate thread that does checkpoint compaction. Think of this like a log structure merge tree, where it's in the background occasionally compacting the log records to reduce the size of it, and it makes deltas of this. And this Microsoft Hackathon does something very similar. All right, so we want to compare what BPF-DB can do against other state-of-the-art systems. So we're going to run a Y6B-like workload using the memtier benchmark, and we just want to measure how many transactions a second, how many operations per second we can push through these different systems. So we're going to compare against the granddaddy of them all, Redis, KeyDB, which is a fork of Redis that Snapchat bought, I think, a couple of years ago. It's basically Redis, but they put a fat lock in front of the hash table. So it's not really, it's multi-threaded, but not really dramatically different. So there isn't any sophistication in it. Dragonfly is a complete rewrite of Redis. Everything's written from scratch, and that is designed to be multi-threaded out of the box. And then obviously our BPF-DB, which is also written from scratch. So along the x-axis, we're going to scale up the percentage of the set commands, or set operations in the workload. So at 0%, it's 100% reads. At 100% over here, it's 0% reads, 100% writes. And then the y-axis here, we're measuring throughput. So out of the box, you see right away that Redis is always going to be the slowest, again, because it's single-threaded. This is not surprising. KeyDB is a little bit better. It's interesting that there really isn't a difference in performance, whether you're doing gets or sets for either of them. And then curiously, what happens now for Dragonfly and our system is that performance gets better as sets go up, and then they get down at this inflection point here. So we thought this is sort of puzzling for a while. Like, why did this occur? Well, it turns out that this is where we're saturating the bidirectional bandwidth of the network, the 10 gigabyte network switch that we were on. And so what happens is, at 50% reads, 50% writes, it's the bare minimum, it's the max amount going in, the max amount coming out. And so that's why you hit 50% exactly. Whereas as you get on the other one side, you're just saturating the one direction. All right, so this means we need to run this again on a beefier machine, which we'll do. But I would just point out, even though we're doing slightly worse than Dragonfly on the downward slope over here, we're actually also running with full serializable transactions, where Dragonfly is not providing that guarantee, right? It's just, it's the last writer wins. So we're running with a full serializable transaction ordering, and we're basically almost able to match their performance. All right, so let's actually, because the name of the conference is P99, it's all about latency. What can we actually get for latency numbers? So in this here, we're just doing a cumulative distribution function, just showing you that the P99 for BPF-DB is, for 10% reads and 10% sets and 90% gets. We're slightly better than Dragonfly and much better than the other two. And we think there's a bunch of additional optimization we can do through partitioning the key space and so forth to reduce this number down even further. So again, this is very early, but we're pretty excited about it. All right, so what's the main takeaway of this talk? So we really think that eBPF is the final thing we need to sort of break out the shackles of problematic design choices of operating systems and start injecting more sophistication into the kernel to allow it to do the things what we want our data system to do. And I would argue that user bypass through BPF is the way to do this. And I wouldn't even start looking at kernel bypass at this point. Some additional work that we want to do in BPF-DB, it's currently not open source because the paper is under submission. We hope to open source it in early 2025. But we think that we can to combine it together with the proxy stuff we showed before and not start doing just-in-time code compilation for SQL queries, which is you're code-genning BPF programs now to run full-fledged SQL queries inside of the system. And now we also understand that not everyone's going to say, oh, I'm going to drop whatever I'm using and switch to a whole brand new system. And so we're looking at using static analysis techniques to automatically identify which components of existing systems could be ripped out and injected down as a BPF program. Of course, the ultimate goal of all of this is to get rid of the kernel entirely, or at least strip it down to be the bare minimum we actually need. It's also known as a unikernel. And basically, where the OS's only job is just to make sure the data system is running properly and not worried about all the other applications that people might actually want to run in a general purpose OS like Linux. And so I'm not the only one thinking about this. So I encourage you to go look at Victor Lies's work out of Germany and his vision of building a data system unikernel. And so with that, I'd be happy to answer any questions. Thank you.